Welcome to AI Frontiers. On October 13, 2025, the machine learning community witnessed an explosion of innovation with 102 research papers published in a single day. This thunderstorm of research across multiple AI domains represents a snapshot of machine learning innovation, telling a story of human curiosity and mathematical beauty as machines learn to see, reason, and understand. Our journey through these 102 papers maps the frontiers of machine learning. This exploration covers field foundations, identifies 5 dominant research themes, examines groundbreaking findings and methodologies, provides in-depth analysis of 3 seminal papers, and considers future directions and implications for the field. Machine learning serves as the engine of modern AI, representing the science of computers learning from experience. This involves pattern recognition in data and building internal models without explicit programming. The technology forms the foundation for voice assistants and medical tools, powers recommendation systems, and drives the entire field forward through bleeding-edge research. The first major theme identified is reinforcement learning and agentic systems, focusing on building AI that can act and adapt. These models learn through trial and error, with capabilities including restarting in non-stationary environments and demonstrating adversarial robustness in gaming scenarios. Agentic web coding with visual self-critique represents a significant advancement toward creating autonomous digital entities. Theme 2 explores generative models and advanced architectures, delving into the mathematics of creation. Research includes elegant collective data movement frameworks and diffusion models for synthetic time series data. Schrödinger bridges provide mathematical foundations for understanding the physics of generation, moving beyond creating images to mastering probability distributions. The third theme addresses representation learning and interpretability, focusing on organizing the AI mind. This involves creating disentangled representations for clear concepts and mapping medical knowledge within language models. Quantum-inspired inference perspectives offer new approaches to understanding what models really know, providing flashlight methods for black box analysis. Key findings from today's research reveal surprising truths and counterintuitive insights. Rowett and colleagues demonstrated that using the exact Hessian matrix causes training failure. Scardecchia's work identified phase transitions in neural networks, while Zhang introduced learning dynamics-aware optimization. These findings challenge assumptions that more precision is always better in optimization, and show biological plausibility can enhance learning algorithms. Several methodologies power today's research and build tomorrow's AI. Reinforcement learning enables complex behaviors, while diffusion models and flow-based methods drive generation capabilities. Graph neural networks handle relational data, and large language models serve as system components. Integration across multiple AI paradigms represents a significant trend in current research approaches. The selected paper by Scardecchia and colleagues, titled Learning by Steering Neural Dynamics, presents a statistical mechanics approach to learning. The research reveals critical phase transitions in networks and proposes a brain-inspired algorithm that operates without backpropagation. Using local plasticity rules for energy efficiency, the work establishes links between network physics and learning capability. Rowan's paper examines the curvature paradox in neural networks, demonstrating that the exact Hessian matrix causes training failure. This finding challenges second-order optimization assumptions and reveals strange loss landscape geometries. The research suggests simpler methods succeed by ignoring certain information, forcing a re-evaluation of optimization theory for deep learning. Gupta and colleagues introduce QLens, providing a quantum perspective of transformers. The work reinterprets transformers through quantum theory, modeling internal activations as quantum state vectors, and layers as unitary probability-preserving operators. Using the Born rule for output probability calculation, the framework offers a new toolbox for model interpretability and analysis. Future directions in machine learning point toward several key developments. The fusion of learning paradigms into unified agents represents a major trend, alongside brain-inspired algorithms for energy efficiency. AI integration into scientific discovery processes continues to advance, while the development of fundamental deep learning theory remains crucial. Hardware designed for biological computation represents another important frontier. This presentation was created through AI synthesis and review processes. Content synthesis utilized the GPT DeepSeek-chat model with text-to-speech generation via Deepgram. Visual design concepts employed Stable Diffusion, and human expert review ensured accuracy verification. Potential oversights in the synthesis process are acknowledged. Key takeaways from these 102 papers reveal important insights about AI's future. The field is learning to embrace messy, dynamic computation similar to biological brains. Simple intuitions about optimization can be fundamentally wrong, and failure often teaches us about model limitations. Quantum and physics perspectives offer new insights, indicating the field is maturing toward understanding rather than just scaling. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by the archive preprint server.